All right, so yesterday I let you know that the answer for x was 34 over 21, the answer for y is 20 over 21, and here's one way of arriving at these values for x and y. What I decided to do was to eliminate the variable x from each equation, and to do that, you want to make sure that their coefficients are opposite numbers. So essentially what you do is you try to figure out what's the LCM of 5 and 2, lowest common multiple, and then just readjust them so that they're opposites of each other. And one way you can do this is to multiply the top row by 2. Okay, so that's every term on the left and also the 10 on the right, which is why it's 10x plus 4y equals 20. And then we can multiply the bottom equation by -5 to get negative 10x minus 25y equals negative 40. And then you can add in column format, which eliminates the variable x and leaves you an equation just in terms of the variable y. And we can go ahead and divide each side by negative 21. So due to the double negative, we get a positive result for y as 20 over 21. Now you could go back and rescale these equations to eliminate the variable y, which will help you solve for x. Or what you could do is, knowing that the variable y is equal to 20 over 21, you can plug that value back into any one of these two equations. And so what you're seeing over to the right here is me plugging 20 over 21 into the first equation to get 5x plus 2 times 20 over 21 equals 10. And then solving for x, we get 34 over 21. Okay, so x is 34 over 21 and y is 20 over 21. And I'm going to say AKA, an ordered pair, 34 over 21, comma 20 over 21. Now I'm going to show you how to solve this a different way using an augmented matrix. Okay, so let's review what that is. So an augmented matrix includes the coefficients of the variables as well as the constants. Now there are two equations, so our augmented matrix is going to have two rows, and there are two variables and then the constant, so there are going to be three columns in this. So I'm going to write out the coefficients, 5, 2, 2, and 5, vertical bar here, and then the constants 10 and 8. And I'm going to operate on the entries of this matrix. And in doing so, we're going to morph this into a matrix that will help us quickly identify what the variable x is equal to and what the variable y is equal to. Now, some of these operations that we're doing relate to this elimination method, that I reviewed for us a moment ago. And I'm going to stick to three particular types of row operations on this matrix, which we will later define as row operations. So this might seem a little like it's coming out of left field at first, all right? But once I define what the row operations are and the kind of matrix that we want to morph this into, it'll all make perfect sense. So I want to just remind us that we can indicate row 1 with lowercase r sub 1 and row 2 with lowercase r sub 2. And what I'm going to do is multiply the first row of this matrix by 1/5. And I'll indicate that with 1/5 R1. Now what's going to happen here is we're going to multiply 1/5 to all of the entries that are part of row 1. Okay, so 1/5 times 5 is 1, 1/5 times 2 is 2/5, and 1/5 times 10 is 2. I didn't do anything with row 2, so I'll just jot it back down as is. What I'd like to do next is I'd like to get this 2 to be a 0. And there is a way to get it to be a 0 by using row 1 in a special way. Now, what we're going to do to get that to be a 0 is we're going to multiply row 1 by -2, which I'll indicate by -2 R1, and then we're going to add those entries to the entries of row 2. Now I want to let you know that when all is said and done, the values that we get will be for row 2. So the row 1 entries are going to remain the same after we do this step. Now, if this is your first time with something like this, I recommend including some scratch work. That way, it's crystal clear as to where these numbers are coming from. And here's one way of indicating your scratch work. Let's start with the -2 times row 1. Okay, the row 1 that we're going to use is the row 1 from our most recent matrix. So I want us to think about multiplying all three of these numbers by -2. When we do so, the first number is going to be -2, the second number would be -4/5, and the third number would be -4. And we're going to add that to the entries of row 2, which are currently 2, 5, and 8. And we're going to add down in column format. -2 plus 2 gives us 0. -4/5 plus 5 will give us 21/5. And then -4 plus 8 will give us 4. So these three numbers are going to be the new entries for row 2. Okay, we'll keep the row 1 entries the same as they were from the most recent matrix. And we've achieved what we wanted to. We got that 2 to be a 0. Everybody good so far? The next thing that I want to do is turn this 21/5 into a 1. And one way that we could do this is by multiplying this second row by 5/21, which I'll indicate as 5/21 R2. So we're going to multiply all the entries of our most recent row 2 by 5/21. That should give you 0, 1, and 20/21. Row 1 will remain the same from the most recent matrix. Very last thing that I'd like to do is get this 2/5 to be a 0. And how we're going to get the 2/5 to be a 0 is by using row 2. So the number that would cancel out 2/5 would be -2/5. So this next step is going to require us doing -2/5 row 2 added to row 1. Now keep in mind, this is only going to affect the row 1 entries. Okay. Now, as with the last operation of this sort, it might be helpful to include some scratch work. -2/5 row 2 is going to look like 0, -2/5, and then we're going to have, it's going to be -40/105, and that reduces to -8/21. We're going to add this to the entries of our most recent row 1. That's 1, 2/5, and 20/21. Oh, I'm sorry, 2. Wait. Now when we add these down, the numbers that we get will be our new entries of row 1. And what you're going to have is 1, 0, and 34/21. So row 1's newest entries are 1, 0, 34/21. And then the most recent row 2 entries are 0, 1, and 20 over 21. Now, have we seen these numbers before? Take a look at our work for the elimination method version of the solution. Where have we seen these two numbers before?
They were our answers.
Yeah, they were our answers for x and y, weren't they?
Yes, sir.
So how can we infer from the matrix that these are values for x and y? Well, keep in mind that the first column's numbers correspond to coefficients of x, and the second column's numbers correspond to the coefficients of y. Now, if we take a peek at this version of row 1, we could write this out in equation format. Specifically, the row 1 from our current matrix would tell us that 1x plus 0y is equal to 34 over 21. The left-hand side simplifies to just x. And boom, that's how we can infer that x is equal to 34 over 21. Row 2 of this version of our matrix would tell us that 0x plus 1y is equal to 20 over 21. Well, this reduces to y equals 20 over 21. And that's how we can link up the value of 20 over 21 to the variable y. So when we have a matrix in this format, or the left-hand side of the vertical bar in this format, we're able to deduce the value of the variables, just by inspection. Now that is a form of the matrix that has some special terminology associated with it. And before we get to that terminology, I want to let you know that there is a name for the process that we took this augmented matrix through. And the name of that process is known as Gauss-Jordan Elimination. Named after the two mathematicians that discovered this. Now, Gauss-Jordan Elimination and Gaussian Elimination are related to each other. Okay, Gauss-Jordan Elimination happens to take a few more steps than Gaussian Elimination, but both will help you to arrive at the values of the variables. They won't change their numbers regardless of which method you use. Now, what I was doing with the rows was based on things that are called elementary row operations, and there are only 3 of these, okay? And they're spotlighted in this box here. The first type of row operation is to multiply an entire row by a non-zero constant. So as an example, one of the steps in that solution on the last page was to multiply row 1 by 1/5. Another row operation is defined as interchanging 2 rows. So this is when you can swap row 1 with row 2 and vice versa. And if you think about it, we can do that with a linear system that's presented to us in equation format in the beginning. There would be no harm in switching these 2 equations with each other. We would still get the same answer. Okay, so a row operation of interchanging 2 rows is legitimate, although we didn't need to do that in our solution. Okay, but I do want to let you know that is one type of row operation. And here's how I indicate it notationally. If I wanted to, say, switch row 1 with row 2, I draw these little arced arrows in this way to indicate that we're swapping the 2. We did do a couple of instances of the third elementary row operation where it's adding a constant multiple of one row to another row. So one step from that last page was -2 row 1 plus row 2. Okay, that's what we mean by adding a constant multiple of one row to another. Okay, this is the constant multiple part of it. Now, you want to get the ones first because you use them to get the zeros. Although you can go out of order a little bit and get zeros first and then get your ones, but it doesn't always work out that way. So I'll actually take you through like a very methodical, step-by-step sort of standardized process that we could all do, just so that there aren't so many options of doing a problem that we get confused about it. So yep, I'll get to that one with one of our examples to come. Is that okay, Joe? No problem. So do keep in mind that when we add a constant multiple of one row to another, it's the row that we're adding the constant multiple to that gets affected. All right, so I'll say affected row. Now I'm going to make a note here. I'm going to say don't do something like row 1 minus row 2. Okay. Sometimes the author is very literal with, or very literal and very intentional with how he writes things out. And when he says add a constant multiple of one row to another, he really means the add part of it. Okay, we want to keep the operation as addition versus subtraction, because if you do R1 minus R2, you might think that this is the affected row, but it's not, because you could rewrite this as negative R2 plus R1, in which case, based on our definition of row operations, this should be the affected row. Okay, I know in some cases it's going to be very tempting to subtract two rows from each other, but always, always, always stick with the addition. Okay, even if that requires the opposite of a row being added to another row. Okay, because we just want to be consistent here, and the row that we're adding our constant multiple to is the real row that's going to get affected. Now the format of the matrix is pretty important for us. Okay, essentially what we do is we take an augmented matrix through these row operations to put a matrix that's either in something called row echelon form, or REF for short, or we put the matrix into reduced row echelon form. And we're going to start with looking at the characteristics of a matrix in row echelon form. And I'll indicate two distinguishing factors. So what I want you guys to notice with all three of these matrices is that they have something in common with regard to their entries in each row. You'll notice that in each row, the first non-zero number is a 1. Okay, so if we look at the matrix given in A, the first entry is a 1. And in row 2, the first entry is not 1, but the first non-zero entry is a 1. This guy right here. If you look at the matrix if you look at matrix B, its row 1 starts off with a 1. Its row 2 doesn't start off with a 1, but its first non-zero digit is a 1, if you go from left to right in that row. And going from left to right in row 3, the first non-zero digit is a 1 as well. Likewise, with the matrix in part C, the first non-zero digit in row 1 is a 1, and the first non-zero digit in row 2 is a 1 as well. These 1s that end up being the first non-zero entries in each of these rows are referred to as leading ones. Okay, so this is the leading one, this is a leading one. And basically, these leading ones correspond to your leading variables that we were discussing yesterday. There's one more commonality between all three of these matrices. Is anybody picking up on something else that's in common with all three of these matrices?
Zeros?
Yeah, exactly. Yep, underneath these leading ones, with the exception of the leading one in the very bottom row, there's a zero. Okay, if you look at the matrix in part B, underneath the first leading one, the entries are all zero. Underneath the second leading one, the entries are all zero. And first leading one in the matrix in part C has an entry of zero underneath its first leading one. And yeah, that is those are the distinguishing properties of a matrix that's in row echelon form. Okay, so just to summarize here, distinguishing properties of a matrix in row echelon form, there are the so-called leading ones. And then underneath these leading ones are all zero entries. So I'm going to say zeros underneath the leading ones. Any questions about that? Okay. Well, there's also a form called reduced row echelon form, excuse me, RREF for short. And there are some similar characteristics between a reduced row echelon form matrix and a row echelon form matrix, but there's one more distinguishing characteristic for a reduced row echelon form matrix. You'll notice that each row has a leading one in all three of these matrices. There are also zeros underneath these leading ones. But you should also be seeing zeros above the leading ones. Okay, in this first matrix, there's a zero above the second leading one. There's a zero above the second leading one. In matrix B, there's also a pair of zeros above the third leading one. And then there's a zero above the second leading one in the matrix in part C. So with a reduced row echelon form matrix, you have the leading ones, you have the zeros underneath the leading ones, but you also have the zeros above the leading ones. Okay, so let's summarize this. So leading ones, zeros underneath the leading ones, but also zeros above the leading ones. Is that all making sense so far, folks? So the yep, go ahead.
Sorry. So in the part C one, there is another one after 1/4, which has a zero above it. Will that be counted or no? It should be the beginning of each row.
The beginning of each row, right? Okay. Right. Yep. So always the first non-zero digit. So yep, the first non-zero number in row 1 is a 1, and the first non-zero number in row 2 is a 1. Anything else that comes after these leading ones, we don't consider. Now, I do want to make an important note. this isn't really a two-way street. And what I mean by that is reduced row echelon form implies that the matrix is also in row echelon form because we have the zeros underneath in addition to the leading ones. However, a matrix that's in row echelon form does not imply that you have a matrix in reduced row echelon form. Okay, because it's possible that there are zeros underneath the leading ones, but there are some non-zero digits above the leading ones. All right, so a matrix that's in RREF is also an REF, but it's not necessarily true that a matrix in REF is in RREF. So on the next page, there's a summary of how you can put a matrix in RREF format, which I tend to do more often than not, because when the matrix is in RREF format, we can just read off the solutions for the variables just by inspection. Now there are going to be situations where a matrix is put into RREF and we might not be able to ascertain the specific solutions because it might have infinitely many solutions. All right, so we'll see a situation of that in just a few minutes. So it says here, the following steps outline how to put a matrix into reduced row echelon form. Number one, if a row does not consist entirely of zeros, then the first non-zero digit in the row is 1. Any rows consisting entirely of zeros must be grouped together at the bottom of the matrix. All right, and sometimes we do have that. We have matrices with a row of zeros, and if we come across those matrices and we're doing this by hand, then we want to move all of those rows with nothing but zeros to the bottom. Number 3 tells you something about the positioning of the leading ones. The leading one in the next row down should be further to the right of the leading one in the row that comes before it. It says, in any two successive rows that don't consist entirely of zeros, the leading one in the lower row occurs to the right of the leading one in the higher row. Each column that contains a leading one has zeros everywhere else in that column. Okay, so remember this is for RREF. So essentially there are two phases that we take a matrix through when we are putting it into RREF. When we go to put a matrix in RREF form, we actually along the way put it in REF format. Okay, so this process of putting the matrix in RREF format though is called Gauss-Jordan Elimination, whereas if it's just row echelon form REF, that's Gaussian elimination. Okay, so the two phases are sometimes referred to as like a forward phase and a backward phase. The forward phase refers to Gaussian elimination, and the backward phase refers to Gauss-Jordan. And what do I mean by that? Well, when we put a matrix in, or when we do Gaussian elimination, we get the leading ones with zeros underneath, but the numbers above the leading ones don't necessarily have to be 0. We come across this form of a matrix when we're actually putting things into reduced row echelon format. And once we get the zeros underneath the leading ones, we then begin the backward phase, which is Gauss-Jordan elimination. And once you've done Gauss-Jordan elimination, that's when you have the zeros above the leading ones. Okay, so Gaussian is when you get zeros underneath the leading ones, and Gauss-Jordan is when you get the zeros above the leading ones in addition to the ones that are below. So with that, I want us to first figure out which form this matrix is in, and then I'll show you how to solve the system based on how the entries of this matrix are presented to us. Yep, I can go back up. Is that far enough? All right, cool. No problem. Let me add in the vertical bar because I do want us to be in the mindset that this matrix corresponds to a linear system. You'll notice that each row has a leading 1, and underneath each leading 1, we have zeros. Do we have zeros above the leading 1, though?
No, is it a forward phase?
This is a
No.
forward phase. Yep. So this augmented matrix has been taken to a forward phase, which means that this is in RREF. We have a couple of options here. We can do some row operations to convert it to RREF, or we can just take a look at what the rows are telling us in the context of an equation to solve for the variables. Now let's imagine that the first column corresponds to the variable x, the second column corresponds to the variable y, and the third column corresponds to the variable z. I'm going to pick on row 3 for a minute. Row 3 tells us that 0x plus 0y plus z equals 1. Okay, so that's 0x plus 0y plus 1z is equal to 1. What does that mean about the value of z?
Z is equal to 1.
Z is equal to 1. And we have a value for one of our unknowns. Now I'm going to kind of work my way up the matrix. I'm next going to look at row 2. Row 2 tells us that 0x plus y plus 2z is equal to 8. Do you think, based on the information we have at this point, we can figure out what the value of y is?
Yeah, can we put 1 in the equation?
Yeah, exactly. Yep. We could actually simplify the left as y plus 2 times 1 is equal to 8. And this gives you a way of solving for y, and you get y equals 6. Let's see what row 1 tells us. Row 1 tells us that x plus 3y plus 5z is equal to -3. And we definitely have enough information to figure out what the value of x is. X plus 3 times 6 plus 5 times 1 is equal to -3. And this is actually why I started off with row 3. Okay, row 3 is the quickest row that gives me information about one of the variables. All right, and this process of taking a variable and plugging it back into a previous row, and then taking those values, plugging them back into another previous row is called cascading. And it's something that you can do when a matrix is in RREF format. All right. When we do a matrix in RREF format, that's when we can just figure out our answers based on the entries of the matrix, just by inspection. So let's simplify here. X plus 18 plus 5 is equal to -3. And solving for x, you get that x is equal to -26. So our solution, can write it out in a couple of ways. We could separate out the variables. X equals -26, y equals 6, and z equals 1. Okay, I'd be happy to accept your answer that way. But this is also known as an ordered triple, -26, 6, and 1. All right, so that's one way of solving a linear system with a matrix that's in RREF format. Okay. The next example, I would like us to go the whole 9 yards and put an augmented matrix in our RREF format. So here our linear system is presented to us already in equation format. Now if we're going to do Gauss-Jordan elimination, we'll have to construct the augmented matrix that corresponds to this. So let's go ahead and start with that. It's going to be 3 rows and 4 columns. In the first row, we'll have the coefficients of x, y, and z, which are all 1s. And then we'll have the constant term of 5, which will be going to the right of a vertical bar. Then the coefficients of x, y, and z in the constant term from row 2. So 2, 3, 5, and 8. And then we've got 4x. Y is not in there, so we would put a filler 0 in for that. And then a 5, and then 2. So not to inundate you with information here, I am going to try to help us keep track of, where, the next phase in the process here. Remember, we want leading ones in each row, and underneath the leading ones, we want there to be zeros, and then above the leading ones, we want there to be zeros. So a little bit ago, I mentioned that there's like a standardized process that you could do, which will help us all perform the same row operations in the same way. The first step of that standardized process is to get a leading 1 in your first row. Now, if you look, we already have that. Okay, so that's kind of a bonus for us. The next thing that you want to do is get a 0 underneath that leading 1. Okay, so what that means is we need to cancel out the 2 and turn it into a 0. We're going to use the fact that there's a leading 1 right above it to help us cancel that 2 out. And there's going to be a row operation that we can do that corresponds to it. It's going to be negative 2 R1 plus R2. Now off to the side, negative 2 R1, we'll turn those row 1 entries to negative 2, negative 2, negative 2, and negative 10. Now we're going to add it to the entries of our current R2, which is 2, 3, 5, and 8. Go ahead and add these down in column fashion. You should get 0, 1, 3, and negative 2. Where do these entries go? Do they go in row 1 or do they go in row 2? They go in row 2. Yep. Very good. So 0, 1, 3, and negative 2. That's the only affected row, meaning that our row 1 from the most recent matrix will stay the same. And so will the row 3. Next, what we want to do is get the second 0 underneath that first leading 1. So that means we need to cancel out this 4. And we're going to use row 1 again to help us out with that. And how we can use row 1 is in this way. We could do negative 4 R1 plus R3. Okay, so off to the side, let's write out what negative 4 R1 would look like behind the scenes. It's negative 4, negative 4, negative 4, negative 20. And then that's going to be added to 4, 0, 5, and 2. So we'll have 0, negative 4, 1, and negative 18. And these are going to be the new entries of row 3, okay? because the row notation that comes after the plus sign is the affected row. So 0, -4, 1, and -18. And we'll use our most recent row 1 and row 2 to fill out the rest of this matrix. And that takes care of our first column. Now what we want to do is get a leading 1 and 2. Okay, do we have a leading 1 in row 2?
Yeah, it's 1.
Yep, we got a leading 1 in row 2. So that's good. And we're actually going to use that leading 1 to get a 0 underneath it. Okay, so we're gonna use that leading 1 to cancel out -4. Does anybody want to type in the chat a row operation that can help us cancel out that -4? Check your sign on the -4R2. So since we're adding the row entries together, I think we're going to want that 1 to be a +4. There you go. Yep. So 4R2 plus R3. The affected row here is R3. For R2, using our most recent R2, can be 0, 4, 12, and -8. And we're going to add that to our most recent R3, 0, -4, 1, and -18. So we'll have 0, 0, 13, -26. And that's going to be our new row 3. So far, so good? Okay, what we'll want to do next is get a 0 above the leading 1 in row 2. So that means we're going to want to cancel out this 1. That's part of row 1. And I'm going to give you guys a moment or two to do just that, okay? Use your leading 1 from row 2 to cancel out the 1 that's right above it. All right, and in just a moment or two, we'll go over the values, and I'll answer any questions if you got them. All right, anybody want to type in the chat how they used row 2 to cancel out that 1. You got it. Negative R2 plus R1. Okay, what you should get from that is 1, 0, negative 2, and 7. And we'll keep our most recent row 2 and row 3 values. So we have leading ones in row 1 and row 2, and we have zeros underneath and above those leading ones. So it's probably not too much of a stretch of the imagination what we're going to have to do next. And that's going to be to get a leading 1 in row 3. And we can use the first row operation given on the last page to help us with that. To turn this 13 into a 1 via multiplication, we'll have to do 1/13 R3. Okay, so 1/13 times 0 is 0. 1/13 times 0 is the current balance in Mr. C's bank account, still 0. And 1/13 times 13 is 1. And 1/13 times negative 26 is negative 2. Upon doing that, we have put the matrix in REF format because we have the leading ones and we have the zeros underneath. So if we wanted to, we could bounce out of the matrix setting into equation setting and do that cascading stuff that I was doing on the last example. But I want to go a little further with this, and I want the zeros above the leading 1 in row 3 as well. Okay, so I'm going to kick these steps off to you. Do it one at a time. Okay, once you get more comfortable with this, you can knock out multiple in one step. But I would like you to get the leading 1, get the 0 above the leading 1 in row 2. And then after that, you can get the leading 1, you can get a 0 above the leading 1 in row 3. That's in row 1. Okay, so your mission, should you choose to accept it, is to get this entry to be a 0 and this entry to be a 0 in our current matrix. All right, give you a couple minutes to do that. I'll check in with you once time's up. So let's go over it. Next row operation you might want to do is negative 3R3 plus R2. Okay, that's going to affect the entries in row 2. Upon doing that, you'll get 0, 1, 0, 4. And last but not least, 2R3 plus R1. It's going to give you 1, 0, 0, and 3. All right. So how does that look to you guys? Is that what you guys got? Woohoo! All right, so let's keep in mind column 1 corresponds to the coefficients of x, column 2 for y, and column 3 for z. And based on this, if we look at what row 1 is telling us, it's saying that x plus 0y plus 0z equals 3. This actually implies that x is equal to 3. Row 2 implies that y is equal to 4. And then row 3 implies that z is equal to 1. I'm sorry, negative 2. There we go. So our final answer is the order triple 3, 4, negative 2. All right, any questions about what we did for this problem? Yep, go ahead.
Sorry about that.
No problem.
This may have you kind of repeat something, but could you explain like the process of how it's going from RREF to REF form and the difference? Like, because I know with REF and RREF, like it depends on the leading zeros and if there's zeros beneath or zeros above. Can you just go through that process with this problem particularly?
Yeah, no problem. So maybe what I have in orange could even help as well. When we get to this point right here, where we have the leading ones and the zeros underneath, that's when we have put a matrix into REF format.
Okay.
And once we reach the point to where we have the zeros above the leading ones, that's when we have fully put a matrix through the RREF format. So every time you start out with a matrix and you arrive at RREF format, there will be a point within your work that the matrix is in REF format. So going from REF to RREF just requires a few more additional steps, and that would be to get the zeros above each of the leading ones.
And it depends on the problem necessarily on whether, you know, if we have to solve a system, it depends on the problem if we have to get it in RREF or REF form.
Yeah, so some problems might ask you to solve with Gaussian elimination, in which case you only have to go up to this far, REF, and then you can jump into equation format. Other problems might ask you to solve the system using Gauss-Jordan elimination, in which case you have to go the full 9 yards to put the matrix in RREF format.
Okay, that makes sense.
Cool.